All right, so on to the last objective of the day. So far, we looked at the different images formed by mirrors. We learned how to draw the ray diagrams and interpret them. But I am fully aware that drawing ray diagrams is a challenge for some people. So instead, what if you could predict those images not by memorizing like an objective 1 and not by drawing and interpreting like an objective 2, but what if there was a different method? In method 1, I would look at the scenario with the person's face in front of some sort of, let's call this a rear view or a side view mirror here. A side view mirror is actually a convex mirror. Okay? So instead of this scenario where I would just memorize and say, well, it's in front of a convex mirror, therefore it's a virtual smaller upright image, or doing method 2 and drawing out the parallel ray and the ray that diverges away from the focal point, right? And drawing the ray that goes towards the center of curvature and using that to interpret this as a virtual smaller upright image. What if we could come up with another way that's not memorizing, that's not drawing ray diagrams? And you know what? We've already done all the math for this when we did lenses. It turns out the reason we're doing lenses and mirrors together is not only because they make the same types of images, and not only because we can do similar methods with ray diagrams, but we can still use all the same equations. So remember from Friday, we have our lens maker's equation that relates the focal length, the distance of the image, and the distance of the object. That's still going to stand. We've got our magnification equation. That's HI over HO. That will still work. You know what? We can also still use M is negative DI over DO for magnification. And we also know that the radius of curvature is twice as long as the focal length. So let's give us a problem here and remind us how to use all 4 of these equations from this unit. There haven't been a lot of equations so far, so these are the 4 that you should expect to be able to use. And someone did ask difference between center of curvature and radius of curvature. The center of curvature is the point at the center of this sphere. If we took your rear or side view mirror and made it a giant sphere, the center of curvature is a point, but the radius of curvature is a distance. And since everything's going to be in centimeters right now, we're just going to keep it in centimeters. Okay, so let's say I've got some sort of problem where I'm looking at a side view mirror and I want to check, I don't know, my face. I want to see something about my face. Maybe my hair is not looking great. And I know that the focal length of this side view mirror is negative 5 centimeters. And if you're thinking to yourself, why would that have a negative focal length? Well, that's easy. Any diverging device, either a convex mirror or a concave lens, any diverging device has a negative focal length no matter what the object is doing over here. And in this case, I'm the object. And let's say we put me at 15 centimeters, that's pretty reasonable distance, in front of this mirror. Okay? And I want to use those to find all the other variables. I want it to find out where the image shows up. I want the magnification of the image. And I want the radius of curvature. Okay, so I'm going to put little boxes around the things I don't know, and let us math. The only equation I have enough information to currently use, or actually there's 2. Doesn't matter which I do first though. Let's do the radius of curvature one. The radius of curvature is twice the focal length. So in this case, the radius of curvature is 10 centimeters. And you can call that negative 10 if you want. Normally, radius, we keep it as positive. Normally, we like absolute value this, but not a big deal. It's 10 centimeters. Let's find where the image shows up. The image can be found using the lens maker's equation, and this is the one that I'm going to ask you be really careful on in terms of trying out your least common denominators here. You can't just take these and add them together, right? Someone looked at this and said, well, can't I just cancel all the ones here and put 15 and that would just be like negative 20? No, you can't. You actually have to least common denominator this. So I'm going to least common denominator 5 and 15 to a least common denominator of 15. So negative 1/5 becomes negative 3/15 equals 1/15 plus 1 over di. Subtracting 1/15 to the other side, that's negative 3/15 minus 1/15 equals 1 over di. That's negative 4 over 15 equals 1 over di. And so let's cross multiply to solve. Di times negative 4 is equal to 15. Therefore, di is negative 3.75 centimeters. And if you are a person that needs reminding here, negative for an image distance means virtual. And hey, that meets up with over here. If di is negative, that means it's a virtual image. That's exactly what I drew for the ray diagram and what I would predict if I went and memorized that chart, right? Finally, let's get the magnification. Magnification, I can either use one of these two right here. I'm gonna choose to use this one since I don't know the object height to get the image height. So magnification is negative di over do. Substituting in, that's negative 3.75 over 15. And wow, that's not going to be useful for me checking out my hair or face, because when I do the math out, 3.75, because those negatives cancel, divided by 15 is showing me a significantly smaller image. No units on magnification. My magnification is positive because negatives canceled. Positive magnification means it is upright. And that makes sense to me because not only was my image upright when I drew the ray diagram, but virtual images are always upright. So I'm glad that all follows. This 0.25 means that it is a smaller face, a smaller image than the original. So besides the checking like that all my parts are there, I think that this would be rather ineffective for checking like my hair or makeup here. Okay, because it looks smaller than the original. In fact, the reason your side view mirror says objects in image may be closer than they appear, well, that's because when your brain looks out the window and it looks at this side view mirror, it thinks to itself, that small car must be far away. But the car only looks smaller because convex mirrors make smaller images. Now that's actually favorable for cars because we want a smaller image so we get a wider field of view, but what we don't want is to think a car is far away when it's not.
So before you go off and try this on your own, here are the 4 equations you should have written down at this point. We have the lens maker's equation that works for both lenses and mirrors. The radius of curvature equation that relates the radius of the sphere to the focal length that it produces. And one important point on F in both cases, both for lenses and mirrors, is that whenever you have a converging device, F is a positive number, and that's true for lenses and mirrors. Whenever you have a diverging device, F is a negative number. Besides from that, all the rest of the variables are straightforward. Height of the image, height of the object, distance of image to mirror, and distance of object to mirror, where M is that ratio. It's a unitless number that tells you both the orientation of your image. If M is upright, it's oriented so that M is positive. If it's an inverted image, M is negative. And it also tells you whether it's larger, smaller, or the same size as your original object. So when you go try problems 7, 8, and 9, you'll be given a problem with some variable information in it. For instance, the height of the candle I could enter for HI. 6 centimeters could be used for DO. You have the ray diagram drawn as a reference on the right-hand side, though it may not be essentially to scale. You'll see. Right. You need to delete this rectangle and replace it with your solution. You can either do that by inserting some sort of picture of your work. You can type up an equation in Google Docs and then copy it into this location. You could also do it in Desmos and take a picture or a screenshot of it and copy it into here. Whatever you decide to do, you can show your work, you can check your answers, and at the end, use your values to determine whether this is a real or virtual, inverted upright, or larger, smaller, same size image. So for instance, seeing that m equals 4, I would be dragging this over to show it's a larger image. All right, best of luck.